Okay. So first, we're going to need the notion of a metric ball. Okay, what is that? Definition. Let x not in a Rn and R positive number. We define B x naught R or BR x naught to be the set of all x in Rn. There are distance R. So let me draw a picture. If this is x naught, you draw this open ball, this ball around it. So a simple example is just the unit ball. Say in R2. So let me make it. So x comma y in R2 are all the points satisfying this inequality. Yes. Okay. Anything else? Do we need to know Schwarz and Trank? Yes, we're gonna. Yes, you will. Yes. So now we will have defined the basic. Okay, let me see. Now, given subset S in Rn, we will break it into its interior, which we will define, and its boundary. No, they're the same. Yeah, different notations. It's just some people write it B1. That's right. Yeah, people have. I wanted to give you both notations because you might see both of them. So what Liang wrote is exactly right. So you can have both showing up. Is that okay, Xin Yu? All right, so we say that x naught in E is an interior point if you can find some radius such that the ball Rx naught, center at x naught, is fully contained in E. So the picture is this is E, and this is x naught, and you manage to find the ball fully contained in E. Okay. Okay. We say that, so that's one. X naught in Rn is an exterior point. If the reverse. So again, there exists some R x naught such that the ball is fully contained on the complement i.e. the intersection with E is empty. So again, let me draw a picture. This is E, and this is x naught, and you can find the ball fully outside the set. So this is E, and then this is E complement. I mean, yeah. ES is, yeah, here I'm using the one from the notes, yes. So E. Then we say that, yeah, let me, just to avoid any confusion, let me write E here. We say that X naught is a boundary point. If for all radius, so for all, you have the following picture. B R x naught intersects both E and the complement. So the picture is, so this is E, and then this is the boundary point, and any ball you draw, no matter how small, it intersects both E and E complement. So that's what we mean by boundary point. Good, so let's do some concrete examples. So yeah, let E be the half open interval 1, 2. then good. Then one interior point is x naught equal to 1.5. Why is that? Is an interior point. Because the ball, for Rx not equal to 0.1, we have 0.1, 1.5 is fully contained in 1, 2. Because what's the picture? So this is 1, this is 2, this is 1.5, and then you have 1.4 and 1.6. So this is the ball, 0.1, 1.5, and it's fully contained in E. Is that okay? Okay. The Ex naught equal to 3 is an exterior point. For the same radius, because for Rx naught equal to 0.1, we have P 0.13 is fully contained in 2 plus infinity, which is fully contained in the complement of E. This is E. Why is that? So this is the picture. This is 1, 2. This is 3. This is 2.9, 3.1. And so this ball is away from E. Okay, so now we have to do the boundary point. The 1 and 2 are boundary points. So let's prove that. Because for all are positive, BR of 1 is the following set. It's the set 1 minus R and 1 plus R. And so this is the picture. And you see that it intersects E and it intersects a complement for all R. So BR1 intersects E because, for example, they both contain 1. So this is non-empty. And it also intersects the complement because contains, let me see, yeah, contains 1 minus r over 2. Right, so it contains this guy, which is not in E. Okay. Okay, same. So BR2 is 2 minus R, 2 plus R, and for the same reason, it intersects E, and it intersects the complement. So boundary of E, boundary, is the set 1, 2. So let me write some definitions. The collection of all the interior points as denoted interior E. Exterior points is exterior E, and the boundary is partial E. So coming back to the example, the interior of closed 1, 2 is the open interval 1, 2. The exterior of closed 1, 2 open is the set minus infinity 1 union 2 plus infinity, and the boundary of 1, 2 is the singleton 1 and 2. Okay. Let's see. Well, I should prove you why this is the interior. So claim. Yeah. Let me try to prove this. Interior of 1, 2 open is indeed 1, 2. Okay, so what do I have to do? Yeah, so for all x not in 1, 2, I want to find Rx so that PR of x is fully contained in 1, 2. All right. So here we are. This is 1, and this is 2. X falls somewhere in here. Now, since X is not 1 and X is not 2, how do you say it? Let D to be the following distance. So X minus 1 over 2 and 2 minus X over 2. All right. So this is this. It will be this guy because you're closer to 1. But if you were closer to 2, say something like this, then this is the one. Okay, so you let this be the distance, and so then the ball BD of X is fully contained in 1, 2. So let's try to do this carefully. You won't have to do it. I just want to do it once for you to see it. So let me see. This is the X minus D, X plus D. And so because 1 is strictly less than X minus D, and X plus D is strictly less than 2. Because from the definition of D, we have this inequalities. So let's do this carefully. So let's see. So 1. So for the first one, we have, this is the same as this, but this follows because you get 1 plus which is true. So I'll leave you to do the other one. Okay. Why is 2 in the closed bracket for exterior if 2 is in the boundary? So I mean, good. Is yeah. So you see here E is closed 1, 2, and so okay. Oh yes. No, you're right. You're right. I'm sorry. Of course, yes. It's open. Yes. Ajit, you're right. Is it okay now? Yes. Thank you. So a general proposition that I'll let you to prove is exactly what he talked about, which is that E is equal to interior of E union boundary of E. And also Rn is equal to interior of E union partial E. So this is disjoint. and then exterior of V. Yes, they're mutually exclusive. Okay. Sang-woo, is that okay? They're mutually exclusive. So, okay, fine. So now let's define open and closed sets, and then we'll take a break. Open and closed. And also what's called the Klopen. We call E in a Rn closed set if it contains so let me not write this. If it contains all of its boundary. I.e., E is equal to interior V union partial E. So the picture is this is E, and it contains all its boundary. We call E in a Rn open set if it contains, if it does not contain any of its boundary. I.e., E is equal to interior of E. So and the picture is like this. This is E. So this is the boundary of E. Okay. So, and finally, we call E in a Rn Klopen if the boundary is empty. If its boundary is empty. And then if you have a situation where, so okay, these are the definitions. Remark. If it contains only some of its boundary, but not all, then it is neither neither closed nor open. So I'll finish with some examples and then we'll take a break. Okay, so the set open 1, 2 is open because its boundary is 1, 2, and it has empty intersection. The set closed 1, 2 is closed because its boundary is 1, 2, and the boundary is fully contained in E. Yes. Yeah, the set the half open interval 1, 2 is neither closed nor open because because partial E intersects both E and the complement. Okay, any questions? And then finally, the set E equal to all the real numbers is Kloppen because the boundary of V, meaning the boundary of the real numbers, is empty. Okay. Guess let me write it. We mean minus infinity, infinity. It has no boundary. Okay. So we say that R is both closed and open. All right, so let's take a small break. We'll start again 12:05, and I'll stick around for questions. Is there a non-trivial example of Kloppen like something other. No, you can actually prove that the reals are the only Kloppen set. You can do this by contradiction. Assume there was such a set, you will get a contradiction. Meaning, so that's a good question. So let me try to figure this out. So um, assume that there was E in a Rn that is both closed and open. I claim that you will get that this will just be the same set. So what was the proof? Let's see. Crashed. So let's see. One second, I'm trying to fix something. All right, my OneNote crashed. So okay, what's going on? So Liang, is there a non-trivial example of Kloppen set? So like we said, right? So you only have the reals and the empty set in the real numbers. In other topologies, there are other things, but we're talking about real numbers with the Euclidean metric. So the only Kloppen sets in R with the Euclidean distance topology. Are the space itself and the empty set. Is that okay, Liang? What else? Yeah, I'm sorry, Kim Young. My OneNote crashed. So you want the proof for interior that 1, 2 is yeah, I will type it in the notes because my OneNote crashed. What else? Isn't the null set? Yeah, the null set is also Kloppen. So the only Kloppen sets. Can a set be both bounded and unbounded at the same time? I mean, no, you can see this, right? So, yeah. So, am I sharing? You know, a set that is bounded satisfies that for all x, there is M, so that for all x in S, you have this bound. Unbounded means that you can find a collection. So for all M positive, you can find some guy in S so that you have the reverse, right? So one guy says there's a global M naught, so that it contains it. And the other guy says, you give me any M, I can find the point XM that is, you know, is either above it or it's below it. So this is unbounded. And this is bounded. Is that okay, Xinyu? Xinyu? Yeah, you can, but a set can, so a set must be either bounded or unbounded, but can a set be neither closed nor open. Yeah, the half interval. One. So, yeah. So S1, 2 is neither closed nor open. Is that okay, Xinyu? Xinyu, is that okay? Okay. What else? For the set 1, 2, what's the boundary for the complement? So the question is, what's the boundary for complement of E, meaning the boundary of a half minus infinity 1 union 2 plus infinity. It will be the same thing. It will be 1, 2. You can in fact prove this. You can prove that in general proposition, a boundary of the complement is equal to the boundary of E. And that's because the definition is symmetric. Is that okay? Who asked that question? Is that okay, Levon? Are we going to link sup and inf with open and closed? I'm not sure quite what you mean. Yeah, I'm not sure. But I think I know what you mean. Later on, yes, we will do something like that for functions. So unbounded if and only if not bounded. That's right. Yes. But is closed open specific to the L2 norm, or can other norms be used? Yeah. So right, the LP norm has the same properties. So in fact, what we're doing is very, very general for arbitrary norms. Like if a set contains a sup and inf, then it's closed. Well, I mean, that requires so many things. So here's an example, Ruja, that this is not true. So example, take, take this, then make it open, then close it. So this is the, so we take a ball at 0, and then we add, little caps, cap 1 and cap 2. Is neither open or closed, but it contains well, okay, let me see. Yeah, I mean, it's not clear what you mean by sup and inf, right? So, yeah, exactly. So it's not, yeah, it's not clear what you mean by sup and inf. You have to decide on some height. So, yeah, so. But yeah, on R, yes, that is true. And I'll leave that as exercise. Um, so, uh, actually, let me see. Yeah, so here another example in R. So take this guy, 1, open it, 2, open it, 3, and then close it. Um, so let S be 1, 2, open, 3, 4. Then sup of S is 4, and it is in S. Inf of S is 1, and it is in S. But S is neither closed or Ruja, is that okay? Yeah. All right, I have to start. All right. So so now I will give you equivalent definitions um, that are also in the book. So you're free to use any one of them. You don't have to prove them. You can just use them. All right. So this is proposition 311. Uh, the subset E in our Ren is called open, is open if and only if for all x in E there exists Rx positive, so that this is fully contained in E. The subset in Ren is closed if and only if, what does it say? Yeah. For every convergent sequence, xn inside E, and xn converges to L in R, then L is inside E. In words, E contains its limit points. Is that okay? And a very useful one is the subset E is open if and only if the complement is closed. So because in the book, the first two are used as definitions, I will just prove the third one, which is in the book as well. So the first two, just use them as definitions, like in the textbook. All right, so one direction. Suppose E is open. Want to show E complement is closed. Okay, so by definition, consider a convergent sequence, Xn inside in complement with Xn going to L in R. Want to show L is in E complement. Okay. We will do this by contradiction. By contradiction, assume that L is not in E complement, which means that L is in E. Okay. What is ITS? ITS. Maybe you mean a WTS. So this is a want to show. Okay, Tongfei. Tongfei. Yeah, I don't have it here because here. Oh, I see. Sorry. No, I just meant its limit. Like it contains, yeah, its limit points. Let me write it in small. It's confusing. All right. All right. But E is open, which means that there exists RL positive such that B of RL centered at L is fully contained in E. So this is E, this is L, and there's a ball fully contained. Fully contained in E. All right, so we're almost done. Now let epsilon be RL over 2. Then there exists n epsilon positive, so that xn minus L is less than epsilon for all n bigger than n epsilon. And this gives you a contradiction. This gives this, how do you say this? This contradicts this because star says that xn, n bigger than an epsilon, is fully contained in here. But xn for all n is part of the complement. And yeah, so this contradicts that because we know E complement and E have empty intersection. So let me draw a picture. So the picture is this is L, and this is x1, x2, x3, xn epsilon, xn epsilon plus 1. This is E. And this is a complement. And you found the ball fully contained. And it says that it says that some of these points fall inside. Okay, so that's the contradiction because xn are all in a complement, so they cannot be in E. Is that okay? Okay. All right, so that's one direction. Conversely, suppose E is closed. I want to show E is open. All right. What does that mean? It means fix x naught in E. Want to find Rx not positive such that BR of x naught is fully contained in E. All right. Recall E is inside interior of E and boundary of E. So if X naught is in the interior of E, we are done by definition. Of interior of E. So the tricky part is, so suppose that X naught is in the boundary of E. I.e., E and boundary of V have non-empty intersection. This will give us a contradiction. All right. Okay, so by definition of boundary, for all Rn equal to 1 over n, we have that the ball center at X naught intersects E, and it also intersects the complement. Okay. In other words, there exists Xn in the like this. In other words, there exists Xn in B1 over n X naught and E complement for all n. Any questions? Okay. All right, so let me see. Good. Claim. Xn converges to X naught. Okay, so let's prove this. Right, so since Xn is in B1 over X naught, we have that Xn minus X naught is less than 1 over n. So indeed, if you fix epsilon positive, take n to be 1 over epsilon, then you get the limit. Okay, so for this an epsilon choice, you get that they all fall inside the epsilon ball. Okay, so Xn is a convergent sequence. And since an E complement is closed, so the limit point will also be in E complement. But we assume that X naught is in E, which contradicts that E and E complement have empty intersection. Any questions? Okay. All right, so now I'm just going to do a bunch of examples. So, one example, any finite set is closed. So let's try to prove this. All right, so I'll do it with limit points. I think that's good. Yeah, why not? I'll do it with limit points. So for xn inside S with xn converging to L in R, want to show L is in S. That's bad notation. Right. Okay. All right. Let's see. So let D be the minimum interdistance between all the points. So let this be the minimum interdistance. So the picture is x1, x2, x3, x4, so on to xn. And we're looking for the minimum distance. Then take epsilon to be d over 2. Okay. Then there exists an epsilon such that an minus L is less than epsilon for all n bigger than an epsilon. Okay. So now, right. So by way of contradiction, assume that, assume that L is not in S, that means, you know, without loss of generality, L is less than x1 plus, so plus epsilon naught. So how do I write this more clearly? Okay, so the distance of L and S is bounded below by epsilon naught. So x1, x2, xn, and L falls within the cracks. Okay. So then, same argument. Let you know, epsilon to be epsilon naught over 2. We get an minus L is less than epsilon over 2. But this is also bigger. So any questions? No? All right. Does this work? Fine. Okay. Second example. What is the epsilon naught? Okay, good. So, so because L is not in S, we know that there's a minimum distance. So if you like, I will write it like this. So take epsilon naught to just be the minimum distance. Because L is not in S, so there is a minimum. So let me draw it a little bit bigger. This is L, this is x1, and there's a closest point x2, and this is the distance. Okay, good, yeah. All right. Second example, a closed ball B10 is closed. Okay, so let's try to prove this. So the easier proof is we will show that the complement is open. It's a little bit easier. So take any x naught in the complement. Want to find want to find Rx naught so that BRx naught, center Rx naught, is fully contained in the complement. Let me write this as a complement and this one as E. So what's the picture? This is the ball. And we pick a point X naught. So what is the complement? These are all the points that are strictly bigger than 1. So let epsilon naught, in fact, I can just write radius. Let Rx naught equal X naught minus 1 over 2. So this is X naught, and this is the ball. Let this and Prx naught X naught is fully contained in the complement because what do we have? So for any y in here, I claim I'll just do it. We have y2 and I want to do reverse triangle. Yeah. So this is called a reverse triangle. In 1D, this one says that A minus B is bigger than A minus B. Let me see if there's any questions. L could be to the left of X1 as well as right. Yeah, L could be on the left of X1. That's why we took absolute value here. Okay. So let's see. Right, so X naught, yes, good. So the picture is you have X naught, and then you have Y, and this distance is less than R, and this is R. So since how do you say it? Okay. So since X naught is let me write it. bigger than 1, you can also get, yeah, I'll leave the details to you. I don't want to get too technical, but try to use this and this to get it. Yeah, it's fine. I have to move on. So, but the picture is clear. So you have 0. And this distance is 1. Yeah. So it's bigger than 1. So we showed that yeah, BR of x naught is fully contained in the complement because all y are in the complement. Yeah, I'll type this more carefully because I want to do some other example. The ball B10 is open. So why is that? Take any x naught in B10. Want to find Rx naught such that that ball is fully contained in the unit ball. So this is B10. You give me a point x naught, and then we have to find a radius that makes it fully contained. Okay. So let's see. Since x naught is in this ball, we have that the norm is strictly less than 1. So let Rx naught be the distance halved. So this is x naught, this is the distance, and you halve it. Claim BR of x naught is fully contained in B10. Yeah, I should do this. Okay. So let me do this. Take y in BRX naught. Want to show that the norm of y is strictly less than 1. Okay, so we have this. We add and subtract x naught. We use triangle. Then we use that this guy is in the ball, so we have strictly less than Rx naught. And then this guy is in B1, this is in PRX naught. So this is strictly less than 1. And we had a definition for this. It was 1 minus x naught over 2 plus 1. Actually, no, I have to keep this. So then you have 1/2 plus x naught 1/2. And then you use that x naught is in B1. So that gives you y2 is strictly less than 1, which gives you that y is in B10. Questions? Now, why can you just take Rx naught to be? Good question. Yes. So let's see why that doesn't work. Suppose you were very close to the boundary. Suppose x naught is this. Suppose this is like, I don't know, some big number like 9/10. Then the ball will go outside because 9/10 plus 9/10 is bigger than 1. Is that okay, Raghuram? 2, we explained it before, but I'll write it in the notes more clearly why we put subscript 2. Good. Next example. The interval, so this is a tricky one. The interval 0, 1, but in R2 is neither open, so it's neither open nor closed. So what's that interval? We're talking about the set x, 0 in R2. So it's this guy. So why is that? Yeah, so take, I don't know. So for example, for x naught equal to 1/2 0, any ball will intersect both S and S complement. So okay, now we're showing why not open. Yeah, why not open? Okay, so let's see. So the picture is this is 1/2 0, and this is the ball, right? And, you know, this is the ball. You know, the element 1/2 R/2 is in the intersection with the complement, and the point 1/2 0 is in the intersection with S. So there is no ball fully contained. In S. Okay. Now the question is, why not closed? Because the set, because S because the boundary points or if you like limit points 1 and 2 are not contained in S. Right? This is a strict inequality. So this is a tricky concept. When we say open and closed, so the remark is when we say open and closed, you have to pay attention to what dimension, what is the topology. You have to specify you have to specify the dimension as well. All right, so we're done for today. I will stick around for questions. Yeah, so that's it. I'll stay here if you have any questions. Okay, so Joseph says, how do we get the limit points 1 and 2? So we proved this, right? In the first hour, we showed why 1, 2 are limit points, boundary points. For S. So this is because for any BR1, this guy intersects for any radius R, BR1 intersects both S and S complement. So this is S, and this is S complement. So it intersects S complement and S. And that was the definition of being a boundary point. Is that okay, Joseph? Oh, yeah, I meant 0, 1. I'm sorry. Yes, I was thinking of the stuff before. Thank you. Yeah, I meant, thank you, yes. Okay. Any questions? I'll stick around for a few minutes. This is like a mini office hour. So you can ask me any questions. It doesn't have to be lecture related. Yeah, I mean, because the office hour, I'm doing it with the TAs, so the TAs cannot do any earlier than that. So is 3 to 4 impossible, or what's the thing? What's the issue? Do you have a conflict? Levon, just email me and then we'll talk about this. Okay. Any other questions? Is 1, 2 the boundary points in R2? So let me see. So for this example, the boundary points are the boundary points for is the set so it's a little bit counterintuitive. So so this is S, but the boundary of S is in fact the entire closed interval. Simply because every element in parcel of S intersects both S and S complement. Yeah, for example, 4. Bin Ying, is that okay? In Homer 2, question 1, do we have to prove that the limit of the sequence is convergent to e to the x? Yes. That's part of the... yeah, you have to use the monotone. You have to use some results there. Yes. Anything else? I'll stick around until 1:10. So you have 3 more minutes if you have any more questions or anything. So I'll stick around for 3 minutes. Just let me know. Can the series, but eventually are monotonic? Yes, exactly right. So when you want to prove that a series is convergent, it suffices to study the tail. So if you show that the tail, is finite after some big N, then you're done.